Hello guys, thank you so much for being with me in another machine learning tutorial video. In the previous videos, we provided sufficient explanations about regression issues. In this video, we will discuss categories. These types of problems are supervised learning problems with the difference that here the output y are no longer continuous. Famous examples of this type of problem are detecting spam emails, detecting whether online transactions are fraudulent or not, or detecting whether tumors are benign or malignant. In these examples, since y has two values, we have two classes. We call these type of problems and categories binary. We can generalize the same. There are other problems that y takes many values. These are called multiple classification. We want to explore the concept of logistic regression. For example, in examining benign or malignant glands, we know empirically that large glands are usually malignant and small glands are usually benign. So we can make a classification based on the size of the glands so that we can predict their benignity or malignancy based on the size of the new glands later. For this, let's try to fit a line to the data. The difference here is that, for example, if the output of the functions with the new input is a number close to 1, we will categorize it in the category of ones, and if it is closer to 0, we will categorize it in the category of zeros. That is, we must consider a threshold. This threshold is at 0.5. We consider a hypothetical boundary at this point, more than which is classified in class 1 and less than which is classified in class 0. That is, the problem is the same as regression. We have considered only one threshold limit. We increase the data. Suppose we have data that is far from other data. In machine learning, these data are called outliers. We consider that threshold again, and in cases where h theta x is higher than 0.5, we classify the class as class 1 and 0 otherwise. We want their outputs to be between 0 and 1, but if the function h we defined is continuous, its range may be from negative infinite to positive infinite. To achieve this, we need to apply another simple function so that the output is in the range of 0 to 1. So our goal is to limit the output between 0 and 1. If we can do this, we call the result logistic regression. There are various functions in the mathematics for this. One of these is the sigmoid or a logistic function. You can see the function formula here. Here, if z is 0, the output of the function will be 0.5. If it is very, very small, the output will be 0. And if the value of z is very, very large, the output will be approximately 1. In this way, we have reached our goal. Another name of this function is a sigmoid function. The word sigmoid means similar to S. You can see that the figure of this function is drawn like S. Then we use this function. We want to use a sigmoid function that passes through this data as much as possible. Now suppose we have obtained such function. Now that we have it, we want to do the prediction. Acquiring the function is the same as the training phase. We need the same threshold limit for the testing phase again, and finally we do classification. If we have outlier data, it does not have a significant effect on the output of this logistic function, and the output amount will not change much. If we use strictly ascending continuous functions, the output difference in outlier data would be too high. So logistic regression is also regression, only instead of fitting a line, we fit the sigmoid function. Now, since the output is always between 0 and 1, I can think of this as an interpretation probability. For example, when the output of the hypothetical sigmoid function is 0.7, we can interpret this number as a 70% probability. That this new tumor is, for example, 70% malignant and 30% benign. That is, we can consider the output as the probability of belonging to class 1. Bernoulli's experiment is an experiment whose result is either success or failure. Here we can consider success as belonging to class 1 and failure as belonging to class 0. We want to further explore the probabilistic interpretation of the output. You can combine these two formulas and have one formula. If you know Bernoulli's explanation, you are already familiar with this formula. Now we want to explain the most similar method, which is a statistical method. We want to determine the thetas in such a way that the product of all of these probabilities is maximized. Here we have an exponential function. We must determine a theta so that this function is maximized. This is the MLE method, or maximum likelihood estimation. Note that these are possibilities. They are between 0 and 1. They cannot be negative. When we are dealing with the multiplication of many numbers between 0 and 1, because the numbers are so small, we usually take the logarithm of it in mathematics. We no longer call the new function likelihood, but we call it log likelihood. Now we need to maximize this new function. If you are familiar with the mathematical rules of working with logarithms, you will probably notice the expansion of this mathematical formula. Now we have to maximize this expanded function. As with other machine learning problems, we need to define a cost function. This cost function exists in machine learning with the difference that it calculates the minimum cost function. So in order for these two functions to be equal, we must multiply this formula by a negative. So this final formula becomes the same cost function that should be minimized. Here each of these inputs is multiplied by a parameter and the results are finally added together. We can also apply function on this output. This function is called the activity function, which we will discuss in the discussion of neural networks. Depending on what f is, we have different algorithms. If f is the same function, y is equal to x, the problem becomes the regression problem. If f is a sigmoid function, the problem becomes a logistic regression. These diagrams are the important forms that we have examined here. We said that we need a decision-making threshold and border. Notice in the figure that when x transpose theta transpose x is positive, the function returns a number greater than 0. So the output will belong to class 1, and otherwise the output will belong to class 0. So this theta transpose x is equal to 0 itself becomes a decision boundary. These are called the decision boundary equation. Let's see this in an example. Suppose we are given this training set and we want to make predictions based on these 4 new data. Here we have written the equation of the hypothesis. We are going to apply a sigmoid function to this as well. Suppose we have obtained the optimal value of the parameters and substituted the values in the relation. We said that when h is positive, the class is 1, and when h is negative, the class is 0. The state x1 plus x2 is equal to 3 is the same linear equation, which is actually the boundary of our decision making. This is a parametric method. In previous videos, we have defined parametric methods. Now that we have the boundaries and the parameters, we no longer need the training data set. Even if the decision boundary is not a linear function, the principle of work will not be different. In this case, the function of our hypothesis must be of higher degrees. We have defined the cost function. We calculated it using the sum of squared error method, and we want to calculate it using the intuitive method as well. Given that linear regression and logistic regression are quite similar and only the activity function is different, we can do the calculations here through the same cost function as the sum of squared errors. Suppose we have the training set and the training sample, and we have considered the hypothesis function in this way. Now we need to define a cost function, and by minimizing that cost function, get the value of theta parameters. Here our function is no longer a convex function because sigmoid is a nonlinear function, and therefore the global optimal solution will not necessarily be found. Next, we want to define another cost function which must be convex, and we must be able to reach the global optimal point. Now we use the logarithmic cost function. Why? To explain, it is enough to draw these two functions. You are familiar with the form of the logarithm z function. The logarithm between 0 and 1 is negative, and considering that we have applied the sigmoid function in the problem, and then we only need this interval. If we multiply by a negative and apply it to 1 minus x instead of x, we get this. When, for example, our data output is 1, and then the error will be 0. The further away from 1, the greater the error. And if 0 is predicted, the error becomes infinite. On the contrary, our explanations are also valid. In fact, we want to calculate the error rate. Y is either 0 or 1. If it is 1, we reach the upper formula, and if it is 0, we reach the lower formula. So this combined formula is completely justified as the final formula. This cost function is exactly the same cost function that we obtained from the MLE method. In that method, we had stated the mathematical proof, and in this method, we justified it intuitively. Now the only thing we have to do is to minimize this function and get the optimal value of the parameters. The minimization method is the same as a gradient reduction, gradient descent actually. Why will we reach the optimal point? Because this formula is convex. I have provided you with the proof of the convexity of this function, but don't worry if you don't understand, because understanding it requires deep knowledge of linear algebra. Here we have calculated the first differential of the cost function as a vector. This can be implemented very easily in Python. In linear algebra, the first differential is called Jacobian. For this reason, it is denoted by J. In linear algebra, we also need the second differential to prove that a function is convex. We must say that its second differential is a positive matrix. For example, the function x2, x in power 2 actually is convex because its second differential is positive. In the discussion of matrices, we must prove that the Hessian matrix, which is the second differential, is a positive definite matrix. We always had this relationship in the discussion of gradient descent algorithm. In linear regression, the figure of the gradient was exactly the same. The only difference is in h theta x, to which a sigmoid function has been added. I have written both methods of vectoring and other vectoring for you, non-vectoring for you. As we said, we use the vector method, which is more optimal. So far, we have examined the classification of two runs. In matters such as email categories, we need three categories: work, family, or entertainment. That means we have more than two categories. That is, the number of categories is k. So we have to generalize the previous statements. Y can contain different values from k different categories. No changes are needed. We just need to convert the multi-class problems into some two-class classification problems. We also know the algorithms are related to two-class classification. We consider one batch as class 1, and then we consider the rest of the data as belonging to class 0. That is, we separate the positive from the negative. We do this for each category. That is, a three-class classification problem became a two-class classification problems. A k-class classification problem becomes a two-class classification problem. Then we need k-classifier. These issues are called one against all issues. It means checking the probability that the input data belongs to the positive class, the probability that the input data belongs to the circle class, and the probability that the input data belongs to the cross class. Finally, we have to choose the maximum probability among them. So far, we have only used the gradient descent method to optimize the cost function. Why? Because until now, the cost function was necessarily convex, and this method worked well. But it is not always possible to define convex as simple cost function. So there is a need for better optimization methods. We will not examine these methods in detail here because they are not applicable to most problems in these fields of machine learning, but we will introduce them. For example, one of these methods is conjugate gradient or BFGS. Which stands for the names of the creators of this method. There are many methods, we don't need them. The advantage of these methods is that they can converge much faster than gradient descent and do not need the learning rate hyperparameters. For example, suppose we have this simple function and we intend to optimize it. We calculate the partial differential of the function with respect to theta 0 and theta 1 and put these together in a vector, and in this way we reach the gradient of this function. Now for implementation, we need a new package called SciPy. if you don't know how these algorithms work, it doesn't matter, because all of the advanced optimization methods are in this package, and you can use them very easily. You can easily define this function in Python, and you can easily define its gradient in Python. And with these two, you can use advanced optimization methods. Before implementing in Python, we also know that at least this function is 0, and this value occurs at point 5 and 5. Now you can use the SciPy package and its features to optimization. For optimization, actually, the first argument is here. The first argument is the function itself. The second argument is the parameters. In this lesson, we denoted the parameters with theta. Here we have indicated these with x, and the name is not important at all. The third argument is the optimization method. These three arguments are mandatory. The fourth argument specifies how to perform the differentiation, and that's all you have to do here. These are two things that are important in this function. The last one returns the optimal point, and the other expression success is true, which indicates the success of the convergence operation. You can see that this method has converged very quickly. If we do not define the Jacobian, it will estimate it by itself. That is the fourth argument is not required. You can implement all the methods in the same way. In the Python files, I have put the implementations for you. Be sure to pay close attention to them. Here I provided you with some references for further studies. If you are interested, pay attention to the Python files, practice to become a high level and skilled machine learning engineer. Have a nice day.